Hello. So a little bit of a change of plan, and we're actually going to go over functions, adding them to our interpreter today, because it can be a little bit tricky. So I'm going to try and change this interpreter as little as possible to add functions. So how I think I'm going to do it is I'm going to add in a lambda, and the lambda is going to have how's this going to work? So a lambda is going to have an expression inside it, and it's going to have the list of things that it binds to. So I could something like, for example, lam. So if so xy to x plus y, that in our syntax would be lam of x y, and then it would be inside there, it would be sort of plus, put it in brackets, var x var y. So that's how we're going to express them. So here I have the Haskell syntax, and here I have our abstract syntax. So yeah, that makes sense. We also need a new type of value though, because the way I see this working is we say things like, we might have expressions that are a bit like let x equal lambda, xy to x plus y, something like that, in x of 10, 12. That's the kind of use case for this. So I'm trying to avoid adding definitions, because we're going to look at definitions soon when we go into recursive functions. But for now, sorry, we're not going to do that yet. So I'm trying to keep it simple, and I'm not going to add in some way of defining a function other than in a let expression as a value. So we've added our lambda, and we need some kind of function value. So the value I think I'll go for is a closure. And a closure looks very much like our lambda, but it has one additional thing. It has the environment. And that's not how you spell closure. And I could really simplify. I could do this in a much sort of simpler way, a more elegant way, where I could have sort of a function value, and I could borrow from Haskell functions, and I could define it something like this, value to value. But I'm not going to do that. I'm not. And the reason why is because this method of doing things is actually mathematically flawed. You have to ask the question, is a function a value, etc., etc., etc. And you can answer yes to that question, but sometimes you have to deal with the Russell paradox, if you're familiar. So that's a problem in set theory, which is of course linked to the questions like, what is a value? And Russell pointed out that it's kind of it's impossible to define a set, a certain set in set theory, and that is the set of all sets that don't contain themselves. And you can kind of see why that's an impossible set to define, because it causes a paradox. So say S is the set of all sets that don't contain themselves. Is S in itself? Is S in S? And if you go yes, S is in S, then you've contradicted yourself, because S is the set of all sets that don't contain themselves. So if you say, okay, no, fair enough, S isn't in S, then it should be, because it is a set that doesn't contain itself. And you end up with the same problem if you add function values. So it makes more sense. Well, does it make more sense? I don't know. But you can completely avoid thinking about that part of philosophy if you just go for this way of doing it. and we capture the environment. Great. So we now need a way of, so the eval function modification is easy enough. Eval of lam list of ident. Oh no, what am I doing? IDs and env equals closure. I've said closures here by accident. Closure IDs env. There we go. Easy line. Easy line. The problem is when we add apply. So this is when things get a little bit of tricky. So apply, and then that's going to be a value. Value. Should it be a value? Maybe not. No. It should be expression. We will evaluate it to a value and expression. So apply is essentially, say I had a function in Haskell to evaluate the nth term of the Fibonacci sequence, fib10. That is like apply. So in our abstract syntax, that would be apply, and then you'd have the lam, get some brackets in there, and it's going to be, say our function is x, an n, if we find the nth term, and then some expression to find the nth term of the Fibonacci sequence, and then we'd just give it a lonely number 10. That would be the equivalent. So apply actually does the evaluation of a function. So we will need to also define that. So eval apply, what's it take in? It takes in our function and it takes in our arguments. So the first thing that we're going to need to do is evaluate the function, and we're going to want to, this isn't too bad actually, but I'm going to make another function apply just to make life a little bit neater, because we're going to be, the reason is if you want to add in like primitive functions, like I could take away minus, I could take away plus, and I could add in lots of extras. I'd make primitive functions. You kind of you'll want it to do something different then. Because for example, I could have primitive functions expressed with the other type of value as a function, as a Haskell function, and then I get a speed up instead of having them all as closures that you have to evaluate. Anyway, enough of that. Apply, it's going to be of type value to value to value. So this is going to take in all of the pre-evaluated things. So apply of, and then we'll map closure. There you go. And I need the values, and then all it's going to do is it's going to eval e. Yes, and it needs to be in an environment that has been elaborated with those values. So in here, I want to, well, think about it. So I need to add to the environment. I need to pair up vals and IDs. So I could probably do that in a really nice way, actually. How's my... Hey, look, so I could go zip, couldn't I? I could zip IDs with vals. So zip, I don't know if we've been over this, it's going to take two lists and it's going to pair them up into a list of tuples, which just happens to be how I defined my environment, which is quite nice. And then, of course, I'm going to need to add the environment to the end. So that should work. I don't know. I haven't planned this lesson at all. Cabal REPL. Oh, parse error. That's an interesting one. I've missed, have I? Oh, I completely forgot to define the body of the evaluation function. So what's this going to be? So I'm going to want to apply, I'm going to call my function apply, f prime and x is prime, where f prime equals eval f in the environment, and x is prime is going to equal yes, eval, I'm going to want to map over it, eval env x's. So I think that'll do it. So here we get the function value, the closure, hopefully, and here we get the evaluated inputs to our function. So what I should probably do as a good programmer is I should say apply of anything else equals an error. So I could say using a value as if it's a function. Okay, let's have a look. Oh, different numbers of arguments. What have I done? Have I... Oh, yep. I need to... And now what have I done? So couldn't match expression with environment. So expected a list of environments and instead got a list of expression. Interesting. Oh, look at that. My expression comes first. So what I'm going to do here is I'm going to say flip. So what that does is at the moment eval, the first argument is an expression, the second is an environment. I now flip it so that the first argument is the environment, which I've provided, and the second argument is the expression. I could use a lambda to do the same thing. And there we go. So let's test it out. This is going to be quite difficult. Writing an abstract syntax is a little bit disgusting. But let's make our expression. So it's going to be let. So let, first of all, takes an ident, so the classic, I'll say add. I'm going to sort of redefine add if you like. So let add, and then the second part of let is an expression. So here it's going to be lam, add is going to be a lambda, and it's going to take in two things, x and y, and its body is going to be add. I'm just going to use the built-in add. I think it was called add. I'm going to say add, and then it's going to be var x and var y. So, yep, var x and var y. And then I need an in. I'm I think that comes at the very end. In, so what am I going to say? Oh, I'll just say apply. I'll put this in brackets. Apply, and then R, it's going to be var add, and then it's going to be was it number? I think it was number. Number 1, number 2. Construction on the scope, expression. Let me just quickly check what my abstract syntax is. Oh, plus. It's plus, not add. So plus, and I think the rest of that's okay. I made the last video quite a long time ago. No, what have I done now? The function apply is applied to 3 arguments. Oh dear, I forgot some brackets, haven't I? Square brackets. It's I can remove these brackets. It takes a list of expressions, not a set of expressions. There we go. Oh, hey. So eval E in the empty environment. Oh, you're joking. Okay, so I found the problem. It was actually a spelling mistake. You see here, I've changed it to a lowercase add, but here I had an uppercase add and a lowercase add. My bad. It works fine, absolutely fine. But there's more to do. What if I want recursive functions? Recursive functions are slightly tricky. I think we're going to go for a sort of an OCaml way about this. So in OCaml, a function definition could be like let f x y equal x plus y. But if I wanted to do some kind of recursive function, I'd have to say let rec f. And it changes how it does the environment. And we're going to really use laziness to get this right. Makes life a lot easier. So we kind of need different types of definitions. So I'm going to add a new type, data defin. And it's either going to be a value, and that's going to be an identity with an expression. Oh, yep, ident. Cool. Or it's going to be a rec value, recursive value, which is also just going to be ident or expression. And the way we treat these is going to be a little bit different so I mean, we're going to, of course, we don't use them at all yet, so we're going to need to work out where to put them. So first thing is, what I think I'm going to do, though, is I'm going to change elab. So at the moment, elab takes an environment, it takes an identifier, and it takes an expression. And we evaluate that expression. But what I think we're going to do is we're going to change it so it takes a definition. So what we're going to do is we're going to do some pattern matching here. So it's definition now. So if it's val I e, pretty much nothing's going to change. But elab env rec ie, things get a little bit interesting. So first of all, the expression has to be a lambda, doesn't it? We can't have recursive values. So I'm going to pattern match further, and I'm going to say lam. I'll just have that as args and expression here. And I'll add a nice useful error message. Elab, don't care, don't care. I think that's it. And then error, only lambdas can be recursive. Cool. Onwards. So Elab is weirdly about to get recursive. So the general idea is that we are going to... Ooh, how are we going to do this? Okay, so we're going to say it equals env prime, where env prime equals, and then we're going to say, so that's got to be of type environment. So it's going to be probably a recursive call to that. Yes. So we'll put in front of env another call to abstract. So we're going to add I, and then abstract, so closure, I think, yes, that makes sense. Yes, args e, and then what else comes? Env prime, yeah. So I realized that this makes very little sense. Essentially here, I mean, I can make this make a bit more sense. So we evaluate, we're going to evaluate essentially this in this environment. So we have a recursive environment, but I skip some steps because there's a lot more boilerplate doing it that way. I know the definition of eval lam is this, which you see here. So that's why you see this side lam and this side closure. That's because I'm simplifying some steps. Now we need a recursive environment because we need access to it when we call I. We need access to I in the environment. And we're always going to need access to that. And you see, because we have the environment here, if I just put env there, env comes from here. It doesn't have access to I. So it's kind of a bizarrely recursive environment. Yeah. But now what we're going to do is we're going to go, and I think, where do we call elab? I think we only call elab here. So we need to change how we do let. So let takes in a definition now. And maybe that's it. Maybe that's all we need to change. Nothing else? Of course we're going to need to change the type up here. So defen. Okay. No, so I've made a mistake here. I put indent instead of ident. That's a harmless mistake. Some deriving cases are missing, so it won't be able to automatically derive. Oh, everything. So line 18, deriving show. Now, aha, a proper coding error. Couldn't match expected type expression to env with. Oh, it thinks it's missing an expression because that's the type of env. So let me have a look back at my definition of elap. Okay, it takes into. Oh, did it used to take in? It no longer takes in an expression because the expression is inside the definition now. Okay, cool. So if we go back here, I will need to make a few changes to this part at least, because now it's not, it's just a val, and that should work exactly the same. Oh, apparently not. Look at that. The definition contains the expression now. So we don't use E. Do we use it at all anymore? No, we don't use E1 anymore. So let's go and make those changes. Okay, and then that's gonna start playing ball with us. Yes, okay, and now we can go up to our big one. Oh, so I need to put that bracket back. Yeah, there we go. Okay, now let's try and think of a recursive function. And this is going to be absolutely horrible because we're working with abstract syntax. So rec this time. So we're going to need an if statement. So let me quickly remind myself what the syntax is for them. Do we have them? Oh, we don't have if statements. Oh dear, let's add them. Let's quickly add an if statement. So if expression. So this is if then else. So that's your guard, that's your expression, and we will also add in, you see, as soon as we add in recursive expressions, we have to add in all sorts of extra things. So bool, val, bool. Now let's add it here. So eval if guard e2 e1 env equals I think it's just match. Match eval g env with, and then, oh no, is it, it's case of, I'm still thinking of OCaml, case of, and then we could say true goes to eval e1 and sorry for being so rushed about this, false eval e2 env. So here what I've done, here what I've done is I've basically gone, well, oh, I have made a mistake as well. That needs to be bool val true, bool val false. So I've said we're going to evaluate G. If it turns out to be true, great. If it turns out to be false, we do E2 instead. I'm also going to need some kind of comparison. So I'm going to add in, our language is getting longer and longer. So I'm going to add in equals expression, expression. So this is going to return, this is going to be an equality check. Oh, I also need to add in bool value. Oh. Val, boolean b env equals bool val b. So I'm going to completely cheat when it comes to equality. You see, for my value, I say deriving show. If I also derive equality, I can then compare, see if they're equal to one another. So, where shall I add that? Eval equals e1, e2, env. Oh no, my alignment. Okay, let me just do this much quicker. Yep. So that's going to equal bool val of eval e1 env equals eval e2 env. So I've added to the language if conditions, equality checks, and booleans. So I've added all that code. There's no way it's going to compile straight away. Okay, I need to add equality to expression as well. So EQ, when it derives that, when Haskell derives that, it does that recursively, just like show. So because I have an expression hiding here, I have to add it here, but I'm also going to have to add it to the definitions because let contains definition. So it won't be able to resolve equality for expressions without definitions. Oh, hey, look at that. Minimal mistakes. So let's try and make... Oh, this can be horrible. Okay, so let's rec. So let's maybe do factorial. Factorial. Now it's going to have an expression. So if actually, hold on. First of all, it needs to be a lambda. Its input is just going to be n, but its expression is going to be if, and then it's going to be equals, and then it's going to be var n, and if that is equal to number 0, then, so I need to be here, I think. Yep. So if it's true, then we're going to return number 1. If not, oh look, we can't do factorial because I haven't added in multiplication. So let's just make sum. So we'll make something that sums up to. So if you give it sum 10, it'll do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. So number 0. If it's false, however, then we'll do add of var n and oh my god, This is so long. Apply. Apply takes in an expression which will just be var sum of, it's not add, it's plus, and then it's going to be minus. So what we're doing here is we'll have an expression minus number 1. Oh, I have to do it the other way. Oh no. Oh no, I've lost. Oh, this is awful. What did it? Not new line. Oh, now it new lines. Oh, I've absolutely no idea what happened to my brackets. Sorry about that terminal mess up. Anyway, so minus, and then it's going to be var n minus from number 1. So you can see the recursive call there. So we're minusing 1. I think that's it. I just need to work out how many brackets I need to add back in. So let me count the brackets so far. 1, 2, 3. Oh no, 1, 2, 3, 4. Oh, hold on. I realised that that needs to be a list. So 1, 2, 1, 2. So that needs to be there. I can remove a set of brackets, but then apply has a bracket around it. Plus has a bracket around it. If has a bracket, I think it's like that. No, let's add some more brackets and see. Yeah, there we go. So, yes. So the type of that is going to be expression to expression, because we've not given letter body yet. We've not given it an in. So I'm going to say stupid variable names equals e, and then I'm going to give it what we're doing. So what we're going to say is we're going to say apply var sum. So we'll sum the numbers 1 plus 2 plus 3. Nice and easy. Number 3. Oh, and I forget again, it's square brackets for the arguments. So val x of this 6. There we go. We've successfully made a recursive function that does summing. So we can change that to 10 if you so wish. And there we go. Recursion. I don't know about you, I think that's quite cool. Bit annoying having to work with abstract syntax, but no matter. We shall eventually move on to making a front end using Alex and Happy. But for now, that should be all. See you next time, and we will actually add monads to our interpreter.